To begin, let's look at some background information about amoxicillin. Its common name is amoxicillin and the molecular formula is C16H19N3O5S. Amoxicillin is a broad-spectrum antibiotic that belongs to the beta-lactam family, which is a subgroup of penicillin antibiotics. It is a semi-synthetic drug, which means it's chemically modified from a natural compound originally derived from the Penicillium chrysogenum mold. It was developed to improve oral bioavailability and increase its spectrum of activity against more types of bacteria. Amoxicillin is commonly used to treat a variety of bacterial infections, including respiratory tract infections, urinary tract infections, ear, throat, and skin infections. Now, move on to the structural formula of amoxicillin. As shown in the slide, the molecule has a complex structure made up of several rings and side chains, which contribute to its function as antibiotic. The IUPAC name of amoxicillin is shown on the slide. Next, let's identify the functional groups found in amoxicillin. The molecule contains a hydroxyl group, a phenol ring, an amino group, an amide group, a carboxylic acid group, methyl group, a beta-lactam ring, and a thiazolidine ring. These functional groups allow amoxicillin to be classified into several homologous series, such as alcohols due to the presence of a hydroxyl group, amines because it contains an amino group, amides from the amide functional group, and carboxylic acids due to the carboxylic acid group. So now let's start with the physical and chemical properties of the amoxicillin. As we can see in the slide, it has a melting point of 194 degrees Celsius and a predicted boiling point which is 743.2 degrees Celsius plus minus with the 60 degrees Celsius. When it comes to solubility, amoxicillin has poor solubility in water, ethanol, and methanol, but highly soluble in hydroxide alkali solution. It is insoluble in benzene, ethyl acetate, chloroform, diethyl ether, and acetonitrile. And in terms of appearance, it is a solid. Visually, amoxicillin is light yellow in color. Its molecular weight is 365.4 mol per kilogram. It's generally stable but incompatible with strong oxidizing agents. The most stable pH range for amoxicillin is between 5 and 7. Now, let's move to the physical and chemical properties of the amides. Amides have relatively high boiling points. In fact, primary amides have higher boiling points than secondary amides with the same molar mass due to the stronger hydrogen bonding. Low molar mass amides are soluble in water, but as the chain getting longer, solubility decreases. Most amides are colorless or odorless solids in room temperature, except formamide, which is a liquid. Amides are polar compound because of the carbonyl and amino groups, which makes them interact strongly with water. Now, we're going to take a look at the structure of the amide. As we know, amides have a carbonyl group that are directly bonded to a nitrogen atom. Depending on how many hydrogen atoms or alkyl groups are attached to the nitrogen atom, we can classify amides into three types, which is primary, secondary, and tertiary. For primary amides, the nitrogen is attached to two hydrogens. For secondary amide, the nitrogen is attached to one hydrogen and one alkyl group. And for the tertiary amide, the nitrogen is attached to two alkyl groups. And for the acid-base behavior, amides are considered as neutral in water, which means they don't act as strong acids or bases, and they don't really change the pH of a solution. And for the last one is characteristic reaction of covalent for amide, which is hydrolysis. This reaction involves breaking the amide bond using water and often under acidic or basic condition.
Benefits and uses of amoxicillin. First, pediatric antibiotic use. Used to treat various bacterial infections in infants, including pneumonia, sepsis, and meningitis. Its effectiveness is influenced by dosing regimens, with higher doses improving the likelihood of achieving pharmacodynamic targets for successful treatment. Next, extensive action used in oral infections. Used to treat odontogenic infections, oral non-odontogenic infections, and as prophylaxis against focal and local infections. It is effective due to its broad-spectrum activity, though caution is needed in cases of pregnancy, kidney, or liver failure. Other than that, targeted nasal drug delivery. Effective local delivery when administered intranasally, which enhances drug concentration in the nasal cavity while minimizing systemic side effects associated with oral administration. Lastly, broad-spectrum antibiotic with enhanced resistant control. Effective against a wide variety of bacterial infections, often used alone or in combination with clavulanic acid to enhance its spectrum and overcome resistance. Benefits and uses of amide structure. First, essential for antibacterial action. The amide is part of the beta-lactam ring. It inhibits bacterial transpeptidase, which is penicillin-binding protein. Prevents bacterial cell wall cross-linking that can lead to bacterial death. Next, high reactivity due to beta-lactam amide. The four-membered beta-lactam ring is highly straight, easily reacts with and inactivates bacterial enzymes. Other than that, specificity to bacterial enzymes. Target bacterial enzymes without affecting human cells. Provides selective toxicity. Finally, contributes to drug stability and oral effectiveness. The amide structure, along with side chains, increases acid stability, allows amoxicillin to be taken orally.
Now, let's look at how amoxicillin reacts chemically, starting with hydrolysis. Amoxicillin contains beta-lactam ring that can be broken down by an enzyme, which is beta-lactamase. Beta-lactamase enzymes catalyzing the hydrolytic ring opening of amoxicillin, which leads to its deactivation. Structural rearrangements of the penicillin-binding protein in the bacterial cell wall may hinder the binding of amoxicillin and preventing it from taking antibiotic actions. The hydrolysis reactions forms amoxicillin penicilloic acid as shown in the chemical equation. Finally, how is amoxicillin synthesized? It's done by acylating 6-aminopenicillinic acid with a suitable compound like p-hydroxyphenylglycine. To make the process more efficient, DCC or EDC is often added as a coupling agent to activate the carboxylic group, and the result is a specific penicillin derivative where the acyl group attached to 6-APA determines the antimicrobial spectrum and stability properties of the penicillin. The chemical equation is as shown in the slide.
Conclusion. The amide structure in amoxicillin is key to its stability and effectiveness, enabling it to combat a wide range of bacterial infections by disrupting cell wall synthesis. This structural feature not only contributes to the drug's chemical stability and oral bioavailability, but also plays a critical role in inhibiting bacterial cell wall synthesis. As a result, amoxicillin remains a widely used and reliable treatment for various bacterial infections.